Hi, this is a lecture on pumps and turbines, and it's kind of a follow-on to the energy equation lectures we've just been through. So here's the energy equation, and I've basically rearranged it so that the pump head is on the left-hand side and everything else is on the right-hand side. I've also gotten rid of the turbine head, but really we could think of this as either the pump head or the turbine head. So let's call everything else on the right-hand side of this equation the system. And think of it as the pump must be in equilibrium with the system. The pump is supplying the energy and the system is using up the energy. That's not always the case. It might be maybe that say the potential energy is helping you, like water's flowing down a hill and then the pump is making it go faster or something like that. So it's not 100% true all the time that all these terms will be the system curve, but in general, let's think of it that way initially. The theoretical pump curve is a constant minus some constant times flow rate squared. So it's an upside down parabola. And here's an example. This is a company. This company is Taco. They produce these pump curves. So this is the model 4010, and it's operating at 1760 RPM for water. And you can buy it with these different diameter impellers inside. And for any given flow rate, you can look over. This is maybe right here is about the best operating point efficiency-wise. Here's the efficiency curves. It's about 750 gallons per minute. It's operating at about 105, 110 feet of head. It would have a brake horsepower, lines are here, of about 22 brake horsepower or something like that. And the net positive suction head would be here, about 13 feet. All right, so the pump curve here, this is what the pump will do. And if we attach a system to the pump, the system curve, the resistance goes up as the flow rate squared, right? The intersection of the pump curve and the system curve, in this example, is here for the 9.5-inch impeller. If we'd bought the pump that came with the 10.3-inch impeller, the operating point would be there. So that's the way this works. So here's a series of, these are various companies. Green Heck is a company that makes fans and things, Marquette grad. That's what their pump curves look like. They all look kind of the same. All right, so let's go over these. The first thing we should think about in a pump curve is there's these similarity rules. So if we change anything in the pump, how does it affect the flow? Well, we've got these really nice similarity rules, like ratio of the flow rates for one setup versus number two setup goes as the impeller rotational rate, ratio of rotational rate, times the ratio of diameters cubed, or the head delivered goes as the ratio of the rotation rate squared times the ratio of diameter squared. The power goes like density squared, ratio of rotations rate cubed, and the ratio of the diameters to the fifth. So let me show you how that would work. So let's say you have this example, a pump which is geometrically similar to the 3.5-inch impeller, the 38-inch impeller model shown below. So it's this curve right here. It has a diameter, the pump that we're looking at has a diameter of 24 inches, and it's supposed to develop 300 brake horsepower at the best operating point, BEP, when pumping gasoline. Determine what the approximate speed would be, the approximate head would be, and the approximate flow rate would be. So the question is asking, if I had this pump and I changed the impeller from 38 to 24, and I changed from water, this is done for water, to gasoline, what would I have to rotate? What would the speed have to be for this? Well, it says here that we're operating at BEP. So BEP is here. That's the best operating point. You can find it by looking at the best efficiency. It's about right in there for this impeller, for the 38-inch impeller. So if I want to know what the new power would be, I would just use my similarity rule. It says here that want to develop 300 brake horsepower. The best operating point's brake horsepower is 1250, so there's my ratio. The ratio of densities, water to gasoline. It was operating at the 710 RPM. What am I going to operate it at? It was at 38 inches impeller, now it's at 24, so I can just solve for the rotation rate. Same with the head. It was generating at this location about 225 feet ahead at 710 RPM with a 38-inch impeller. When I change it to the 24.8-inch impeller and I rotate it at this 1080 RPMs, it should generate about 208 feet of head. What's the flow rate? Well, it was operating at about 20,000 GPM and at 710 and with an impeller of 38. I changed the impeller, I changed the flow rate, the rotation rate, and my flow rate would drop to 770, 7,700 GPM. All right, so that's the way these similarity rules work. Let's talk about the horsepower itself. So recall that theoretically, or ideally I should say, density times gravity times flow rate times the horsepower or the head of the pump would give me the power. The actual power I would get from the pump curve, because that's data. The pump curve is generated with data. It's called the brake horsepower. That's because that's the power that I have to supply to the pump. Then there's losses associated with pumping. We'll talk about that in a second. And the equation for that is omega times torque, the rotation rate times the torque. So let's talk about the isotropic efficiency. You remember there's a first law of energy, but the second law says that really you can't use all of the energy you found in the energy equation. So a pump efficiency, the isotropic efficiency, is I always think of each device. If you had a pump and you wanted to pump water from a lake up to some higher elevation, you would use the energy equation and you would calculate how much energy it would take. But that's an ideal calculation. There's going to be losses within the pump itself. How much are the losses within the pump? So in reality, you're going to have to put in more than the ideal amount, right? So you have to put in more, the actual will be larger. So it would be ideal over actual, right? So the ratio of ideal over actual will give you something less than 1. And the previous slide, we defined what those were, and there is the equation for it if you need it. A turbine's the same way. If I have a reservoir of water and I'm going to lower the water, drop its potential energy and run it through a turbine in order to generate energy, I'm going to calculate, wow, I can generate a whole lot of energy. But the actual energy that I generate will be less than the ideal calculation that I get. So in this case, its actual over ideal will be less than 1. See, it's just the opposite as these two. So I don't memorize what they are. I just remember that I'm always going to be on the losing end of the isotropic efficiency relationship. And then these guys are just the inverse of those. All right, let's talk about cavitation for something. Net positive suction head. That is the amount of head you need to supply to a pump so that when the pump draws the water in, it sucks it in, it doesn't accidentally pull a hard enough negative pressure on the water or on the fluid such that it boils the fluid, such that it vaporizes the fluid. So net positive suction head is something to be avoided. So the required net positive suction head, right, to avoid cavitation, the actual net positive suction head must be greater than the required net positive suction head. You get this from the pump curve. All right? The required, it comes from the pump curve. If I look back at a pump curve right here, there it is. If this were my operating point, I would read that net positive suction. I'd read up till I hit that net positive suction head and read it over. That pump requires 15 feet ahead at the inlet or you're going to boil the water. All right. And in general, you need to, the actual net positive suction head will be the inlet pressure minus the vapor pressure, because it could be that the vapor pressure is quite low for a given fluid or quite high, so you want to account for that vapor pressure. And what's cavitation? Like I said, it's boiling. You can see it here on the backside of a blade, such as this impeller, where you generate very high pressure on the top side and low pressure on the bottom. You can actually cause the water to jump into the vapor phase. And what happens is when the bubble collapses, it can create a jet of water that'll pit your blade. And so you can end up with a blade that's pitted and really just eats away your impeller due to this bubble collapse phenomena. Here's a picture of it right here. It's kind of cool looking, showing this jet that's generated. All right, enough of that. Try out some problems. Talk to you later.